So, what's the theme for today? Today, we are going to learn a very beautiful topic, bit manipulation. Okay, so the great thing is that it's a really beautiful topic. I mean, really beautiful topic, handy with so many cool tricks. Have you guys heard of a topic called as dynamic programming with bit masks? So this is, seemingly, usually it's said that it's a hard variation of DP. And those people who understand bit manipulation, for them, it is quite easy. Okay. Similarly, problems that have to do with combinations or subsets and things like those, there also bit manipulation plays a huge role. Okay. So we will see that what is the magic of bits and how does it, help us. But before that, before you start manipulating the bits, because we all know, all of us know what is a bit, all of us know what is a byte. So I'm not going to talk about the things like 1 byte contains 8 bits. No, I'm not going to talk about those. We all know that if something is a bit, its value can either be 0 or 1. Now, this is one great thing about it. Something which can have limited number of forms is quite less confusing and it is quite easy to operate on it. See, what I mean by that is if something is an integer, it can have infinitely different values. If something is an ASCII character, it can be anything in between maybe A to Z and several other ASCII characters. So it can have several different forms. But when you talk about a bit, it is so pure, it is so nascent. I mean, it can either be 0 or it can be 1, nothing else. No bullshit, right? So this is something which is great about it. And this makes, a lot of problems very much solvable at the level of bits at the level of bits. And we are going to see that today. But before that, before you do bit manipulation, you have to know about the important bitwise operators. So you guys already know about arithmetic operators, right? All of us know that we have got addition, multiplication, division, and subtraction, multiplication, and also sorts of things. These are all arithmetic operators. What are the different bitwise operators? Can you guys give me some quick example of some bitwise operators that you guys have used? Yeah, so and yeah, many of you are mentioning that's right. And or XOR, not, and all these things, right? Okay, so tell me one thing. Is this thing, this and, we all know this is and, right? So is this and a bitwise operator? No, this is a logical and. Okay, this is logical and. Similarly, this or is logical or. They are not bitwise and or an or. Bitwise and is a single ampersand and bitwise or is a single pipe. Okay, and what is bitwise and? So if there are two bits, let's say B1 and B2, then the and will be 1 if and only if both of them are 1. If one of them is 0, the result is going to be 0. If both of them are 0, then also the result is going to be 0. Similarly, when we talk about OR, if we are taking OR of B1 and B2, OR means that if one of them is 1, the result will be 1. So if let's say this is 1 and this is 0, or this is 0, this is 1, or both are 1, in that case, the result will be 1. Only if both are 0, the result will be 0. Right? So this much all of us understand about, bitwise and bitwise OR. Now, if you take any two integers, so let's say your first integer is x equals to 3 and second integer is y equals to 5. And now if you take x and y, how do things work? Then this AND operation is applied bit by bit, bit by bit. So just imagine that x, which is 3, is written in its decimal format, which is, how much is it? It is just 1 1. This is the binary, the binary representation. The binary representation of x is 1 1, right? And similarly for 5, it is 101. So if you take an AND, you can append a 0 over here. So this AND happens bit by bit. So this and that is going to be 0. This 1 and 0 is going to be 0. And this 1 and that one is going to be 1. So what is this? This thing is 1. So I would say that 3 and 5 is equals to 1. That's the result. Okay. Similarly, when you take or operation also happens like that. If you want to take an or, that also happens bit by bit following this particular rule. Okay. Now, one great thing about bitwise operators is that they are ultra fast. They are very, very fast. Okay. So if a lot of people, they compute the power of 2 in this manner. They use POW 2 power n. Or they at times they write their own for loop to compute 2 power n. I mean, they run a loop for n times, and that is how they do it. But have you seen some people writing things like this? How many of you have seen expressions like these? And what exactly this expression is? So this thing is literally called as a bitwise left shift. And there is a brother of this, which is right shift. This thing is called as right shift. But guys, at this point of time, I'll just stop you for a while because I want to touch base upon a beautiful concept. So I'm pretty sure that if you are a C++ programmer, you must have used this operator and that operator somewhere else also. Tell me, come on. At what other places have you used this? Yes, excellent. You have used them with cin and cout. Very good. So you must have used things like cin x, isn't it? Cout, whatever, hello world, whatever it is, right? So what is this? I mean, when you use this operator with cin, when you use this with cout, it performs a different job. I mean, it either scans from the console or writes to the console. But when you use this with integers, it performs a different job. Now, what is this phenomena called as? This phenomena is called as, yes, very good. It is called as operator overloading. And this is a great, great concept of object-oriented programming languages, right? Where the same operator, if used with something, behaves in one manner, but when it is used with something else, let's say you use this with cout, then it is used for printing. But when you use it with integers, it behaves in a very different manner. So this is called as operator overloading. And this is not the first time where you are seeing operator overloading. You have seen it multiple times. Trust me. You have seen it with addition also. When you do 5 plus 3, the result is 8. But when you do 5 plus 3, what is the result? What is the result in this case? Yeah, it is 53. So this addition operator behaves differently when applied with strings and differently when applied with integers. So this is a side thing, but I could not resist talking about it. So I talked about it. So do you guys understand what is operator overloading before we just cut this and move ahead? Okay, that's awesome. So now let's come back to our left shift operator. What is left shift operator? I mean, it's pretty easy. Let's say there is a number n whose binary representation is something like this, 1010. Okay. Now, if you left shift this number by 1 unit, let's say you are saying that, hey, this number n, I want to left shift this by just 1 unit. And this should be the new value of n. Then by left shifting, what happens is that all of these bits are shifted by one unit towards left. So this one comes here, this 0 comes here, this one comes here, this 0 comes here, and at this position, one extra 0 comes. Now, if you clearly take a look over here, what is the decimal equivalent of this? So this thing is 2 and this thing is 8. So it is 10. And what is the decimal equivalent of this? This thing is 4 and this thing is 16. So it is 20. You can clearly see that left shifting by 1 unit has doubled the number. And this is exactly what happens. So if you left shift something by 1 unit, that number becomes 2 times of itself. As simple as that. So this thing is equivalent to writing n equals to n into 2, but it is faster. Okay. So do you guys all understand what left shift actually does? It simply shifts all the bits by 1 unit towards the left and puts one extra 0 all the way towards the end. As a consequence of this, the number doubles. And why it doubles? It's a common sense. I'll tell you why it's a common sense. Because this number, how it is represented? It is represented as This 0 is 0 into 2 power 0. This 1 is 1 into 2 power 1. This 0 again is 0 into 2 power 2. And this 1 is 1 into 2 power 3. Now when you are left shifting, with these bits, their powers will be incremented by one factor of 2. Don't you understand that? Yeah, you would definitely understand. Because if this 1 over here was corresponding to 1 into 2 power 1, here it would correspond to 1 into 2 power 2. Similarly, this one here, if it was corresponding to 1 into 2 power 3, here it would correspond to 1 into 2 power 4. So this thing gets a factor of 2, this thing gets a factor of 2, everything gets a factor of 2, and at the end there is 0. So the number becomes 2 times of what it really was, right? And if you left shift the same number by 2 units, if you write n equals to n left shifted by 2, what is going to happen? So just imagine this 1010, if it is left shifted by 2 units, imagine this 0 came all the way here, this 1 came here, this 0 came here, this 1 came here, and then 0, 0. So this thing is now going to become 10 into 2 into 2, right? Yeah, so it will become 4 times of what it is. So it basically means that if there is a number n which I happen to left shift by j units, then that number n actually becomes n multiplied by 2 raised to the power j. So it is, both of these statements are equivalent. And this is the purpose of left shift. So how many of you now clearly understand what is left shift? Can we have a quick yes, no, whatever it is? Yeah, simple enough, right? Okay, awesome. The way you have got left shift, you also have got right shift. So what do you think right shift does? So let's say there is a number whose binary representation is 1, 0, 1, 0, 0, something like this. Exactly. So right shift is for the purpose of, moving all the bits towards right side by 1 unit. So this bit comes here, this bit comes here, this bit comes here, this bit comes here, and the last bit is just dropped. It is dropped into the sink. Oh, sorry. This 0 came here, this 1 came here. It was 0, so my bad. This 0 comes here, and then this 1 comes here. And the last bit is just dropped. So when you do something like this, you can clearly understand that everything is going to lose a factor of 2. So if here this 1 represents 1 multiplied by 2 power 2, here this poor 1 will represent 1 multiplied by 2 power 1. Here if it represented 1 multiplied by 2 power 4, here it would represent 1 into 2 power 3. So if you right shift something by 1 unit, that is just like dividing by 2. So if I say that, hey, this is n, and I'm going to do something like n equals to n right shifted by 1, then this is equivalent to doing n equals to n divided by 2. And the same logic, if I say n is equals to n right shifted by j, then this is equivalent to doing n equals to n divided by 2 raised to the power j. So this was all about left shift and right shift, and they are going to come very, very handy to us in some time. So just remember them. Just remember them at back of your mind. And now let's quickly move on to the another one, which is XOR. This is a very famous one. All of you must have heard of it, right? How does XOR behave? So let's say there are two bits, B1, B2. If you're taking their XOR, then when is the result 1? The result is 1 if both the bits are different. And the result is 0 if both the bits are same. Yeah, very good. So that is how it is. So, I mean, if both of them are 1, 1 or both of them are 0, 0, the result will be 0. And if they are 1, 0 or 0, 1, the result is going to be 1. That's the simple idea. And this is something which is, I mean, truly very useful. Okay, at this point of time, I'll tell you one more thing. All these operators like bitwise AND, bitwise OR, bitwise OR, they are, they can be applied in any order. So what I mean by that is, if you are taking, let's say, A and B and C, it's same as doing B and A and C. So you can just take the AND operation of these numbers in any order. And it is true for this also and that also. You can think about it because it happens at the level of bits. Okay, it happens at the level of bits. So even if you redistribute those bits, the things are not going to change. The result is not going to change. Okay, so what we'll do is we'll go ahead and pick our first question. And it's a very easy question, but it's a very famous interview question. So we will quickly pick that up. The question simply says that you are given a number. Okay, this number could be anything. Let's say it is 19, for example. We have to count the number of set bits inside it. How many set bits are there inside it? What is the meaning of set bit? It simply means that how many bits are 1. Okay. So can you tell me in 19 how many bits are 1? So the representation of 19 would be something like this: 1 0 0 1 1. This is 1. This is 2. So 1 plus 2 is 3. And 4 8 16. Yeah. So this thing is 19. And here you can see that there are 3 ones. So my answer should be 3. So what is the way to solve this question? Yeah, there is a very well-known way, and I see that many of you know about that. Now just think of it, what could be the brute force way? I mean, let's say when you saw this question for the first time on LeetCode or anywhere else, then what was the first thing that kind of struck your mind? What was the first way? So I'm pretty sure that way would have been continuous division by 2, isn't it? Because if you have a number, let's say 19, you must have learned in your first year or somewhere else that how to convert that number into its binary representation. How do you do that? You do that by repeated division with 0, correct? So you basically take a mod of this with 2 and you see it is 1. So you say that the least significant bit is 1. And now you divide by 2. So when you divide by 2, this 19 by 2, it becomes 9. And then again you take a mod of this with 2. It comes out to be 1. So the next bit is 1. Again you divide by 2, it becomes 4. Again you take a mod, this time it is 0. So you put 0. You divide by 2, it is 2. Again you take a mod, it is 0. So you put 0. Now upon division it becomes 1. Again you take a mod, this is 1. And when you divide, it finally becomes 0. And this is where you stop. So this is what you get. So the easiest thing is that I can keep dividing that number by 2 until it becomes 0. And at whichever point of time the remainder comes out to be 1, I'll simply do count plus plus. And that count would be my answer. Is this approach clear to everyone? What would be the time complexity of this approach? So here you can see you have a number n and you are continuously dividing that number n by 2. So this thing is going to have a complexity of log of n base 2. I mean, any number, if you keep on dividing by 2, after log n steps, it would become 0 for sure, right? So this is one trivial way to solve this question. Now, there is a smart way to solve this question. Now, for that, let us first build our intuition, because everything is about that. So what could be our intuition for this? Let's understand. Tell me one thing. Any number which is a power of 2, how does its binary representation look like? Its binary representation is 1 followed by all zeros, isn't it? Yeah. There is exactly one bit which is 1, because we know, right? Because we all know that in any binary representation, if a particular bit is 1, then it represents 1 multiplied by 2 power something. So if this is jth position, it is 1 multiplied by 2 power j. So if a number n is actually a power of 2, then its binary form will have 1 and everything else will be 0 after that. Before it, anyways, everything is 0, right? So that would be the representation. Now tell me one thing. How will the binary representation of n minus 1 look like? Given that n is a power of 2, how will the binary representation of n minus 1 look like? Yeah. So it will be 0 followed by everything 1, 1, 1, 1, 1. And this is a very simple but very profound observation which you should keep as an envelope at back of your mind. And I'll explain, don't worry about it. Let's take an example. Let's take a number 15. Okay. Can you tell me the binary representation of 15? 1, 1, 1, 1. This is what it is if I'm not wrong. Can you guys verify? Yeah, it is like this. And what is the binary representation of 16? It is 1 followed by all zeros. I'm just appending 1 0 here for convenience. Do you see that this thing is a power of 2? And this thing is power of 2 minus 1. Can you see that? So what I'm trying to show you is whenever you subtract 1 from a power of 2, I mean, if this number is n, it will have a binary format like this. And the binary format of n minus 1 will simply be this one gets toggled to 0 and every other bit gets toggled to 1. So it's basically, it can be thought of as a complement of this, isn't it? Because if you had a 1 here, it becomes 0 and all the zeros becomes 1s. Can you notice this thing happening here? How many of you can notice it? Yes or no? Now, this is not luck by chance. Nothing is luck by chance. Okay, there is a very strong, solid logic behind it. And I'll tell you how. See, any number whose representation is all ones, everything is one. Everything is one from 0th bit till jth bit. What will this number actually represent? So if you try to write it, you will say that, hey, this one is contributing as 1. This one is contributing as 2. This one is contributing as 4. I mean, that is how it is, right? 2 power 0, 2 power 1, 2 power 2. And then this one will be contributing as 2 power 3, which is 8. And then at jth bit, it would be contributing as 2 power j. So this thing is nothing, but it is the summation of 2 power 0, 2 power 1, 2 power 2. Now tell me quickly, does it remind you of something? Which kind of progression it is? It is geometric progression, which you have studied in your classes. And what is the sum of a GP? Sum of a GP is a multiplied by r raised to power n minus 1 upon. Do you remember this formula? How many of you remember this formula from your 10th or 11th or 12th class? Right? Okay, very good. So what is a here? A is the first term. So what is the first term? The first term is 1. So 1 multiplied by common ratio. Common ratio is 2 raised to power n, where n is the number of terms. Number of terms are going from 0 to j. So how many terms are there? J plus 1 minus 1 upon r minus 1, which is 2 minus 1. What is this? This is some power of 2 multiplied by 1. Sorry, minus 1. So what I can say for sure is that if you have a number whose binary representation is like this, then this number is minus 1 of some power of 2. So from here, the key thing I want you guys to literally remember is that if something is a power of 2, it is 1 followed by all zeros. And if something is this minus 1, then it is 0 followed by all ones. How many of you are perfectly convinced with this thing now? Yeah. Now let us see how this can help us to beautifully solve that question where we had to find the count of set bits. Let us just see that in action. Okay, so let us say you have a number n and its binary representation is of this form 1 0 0 1 0 0 0 1 0 1 0 0, something like this. Okay, so this is some number and you have to count the number of set bits. So how many set bits are there? So you can see 1 2 3 4. So your answer should be 4, right? Now see, this entire number can be written in a different style. In which style? I can say that, hey, this number is the sum of plus, sorry, I didn't mean this thing. Let me erase it. 1 0 0 0. And then before it, everything else is 0. See, it's pretty simple to understand. Uh, this thing would be representing some number n, right? Now, if you look at this From the end, just find out the first one, where the first one is located. Now, if you just focus on this thing, can I say this thing would be a power of 2? Yes or no? Because if you're finding the first one from the end, you're finding first one from the end. And if it is here, that means how does this part look like? This part looks like 1 followed by all zeros. Now, this little part that you have here would be some power of 2 for sure. I mean, if this position is jth position, then this little thing would be 2 power j. So if I just turn this off for a while from here, I can say that, hey, this number which is given to you is this thing followed by 2 power plus this plus 2 power j, which is that number. Now, let me tell you what I'm trying to say. If you try to find out the value of n minus 1, what will happen? You are subtracting 1 from this number. Subtracting 1 from this number. So when you subtract 1 from this number, just imagine that that 1 is being subtracted from this, because this is the final part of it. Now we all know whenever we subtract 1 from a power of 2, what happens? Yeah, this one becomes 0 and every other 0 becomes 1, 1, 1, 1, 1, 1, 1, right? So what will be the value of n minus 1? If you try to write down n minus 1, it will be 1 followed by 0, 0, 1, and then 0, 0, 0, 1, and then 0. And now this part will get converted to 0 followed by all ones. Now imagine if you take n and n minus 1, which is the bitwise end of n and n minus 1, tell me what will happen. If you focus your attention on these 4 bits and these 4 bits, are they all complement of each other? I mean, the toggled form of each other? Yes, of course, yes. Because we all know that if something is a power of 2, and if you subtract 1 from it, the 1 becomes 0 and the zeros becomes 1s. So if you're taking an AND of this and that, then in one shot, all these 4 bits will vanish. If they vanish, what does it mean? It means that you will end up getting 1, 0, 0, 1. So it's so far intact. Then 0, 0, 0, 1, 0, 0, 0, 1. And then this 0. And then the last 4 bits will vanish. They will become 0, 0, 0, 0. Right? Now imagine. So now your new value of n, let's say, is this. Now again, once again, if you try looking at n minus 1, how will it look like? How will n minus 1 look like now? You guys can quickly guess how it will look like. This is the power of 2, right? So n minus 1 will look like 1, 0, 0, 1. So far, all right. 0, 0, 0, 1. Sorry, 0, 0, 0. And then this part will get converted to 0 followed by 1, 2, 3, 4, 5, 5 ones. Now, if you take an AND of this and that, can you tell me what will happen? All these things will vanish in one shot, right? And the value that you will get will be 1, 0, 0, 1, 0, 0, followed by all zeros. How many zeros? 6 zeros. 1, 2, 3, 4, 5, 6. Right? So do you see what is happening? Now let me correlate. Let me just quickly correlate. If you have a number, that number always has a tail, which is a power of 2. The tail is always a power of 2. What I mean by tail, I just somehow find out just to show you the first one as found from the end. So this is the tail. And of course, this tail will be some power of 2. So if you do n minus 1, what will happen is that this tail is going to rupture. When I say it is going to rupture, what I mean by that is that all these things will remain intact. And this thing will become 0, and everything else will become 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now you exploit this fact. How do you exploit this fact? You quickly take n and n minus 1. When you do so, these entire things go off in one shot, right? Because that is how AND works. This one, this 0 will AND to 0. And these zeros, these ones will AND to 0. So what you will end up getting will be 1 followed by 0, 0, and followed by these all 0, 0, 0, 0, 0, 0. Right? Now, once again, if you find out n minus 1, how will it look like? 0 followed by all ones. And this time, if you take n and n minus 1, tell me what will you get? What will you get? 0, exactly. It will be 0. So yeah, let me read through some chats. So Ayush is saying for this number needs to be even every time, right? No, 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 not at all. I mean, your number n could be anything. See, your number n could be even 1, 1, 1, 0, 1, 0. What is this? Let's say, okay, your number could also be like this. Let's say something like this. So here also it is going to work. Because here, if you take a look, what is your tail? Your tail is this. Your tail is this. And so if you find out n minus 1, what will happen? This thing will become 0. And after this, there is nothing. So nothing happens to that. So n minus 1 will have this value. Right? And now if you take an AND of this and that, what will happen? You will end up getting 1, 1, 1, 0, 1, 0, 0. So do you see that these two bits have gone off in one shot? Right? Similarly, again, if you find out n minus 1, you are going to get 1, 1, 1, 0, 0, 1, 1. And now again, if you take an AND of this and that, these three bits will go off in one shot. Okay? So can you tell me how many operations will happen? How many operations will happen by the time your n becomes 0? The number of operations which will happen will be equal to number of set bits. Number of set bits, as simple as that. Why? Because if you have a number, let's say this is your number, for example, okay? Now, the moment you find out n minus 1 and take an AND, all these things go away in one shot. And what you get is this. So this was just one operation. In the next operation, when you again take an AND of this with n minus 1, all these things go out in one shot and it becomes 0. This was your second operation. So the number of operations will be exactly equal to the number of set bits that you had in your input. As many set bits, those many operations. If you just have one set bit, let's say your input is this, then in only one operation's job will be done. Because the moment you take the AND of this with n minus 1, the result would be 0. Do you get it? How many of you understand this thing? So basically, idea behind this is super simple. That keep taking AND of n with n minus 1 until it becomes 0. So we would say, let there be a count which is 0. And while n is not 0, we will simply modify n as n equals to n and n minus 1. And we will do count plus plus. And finally, we will return the value of count. Okay, just to summarize everything, see, the idea is pretty simple. All of you got this idea, right? Because what was the idea? If you have a number n, it will be of some form. And then let's say the last one from end is this. So if it's the last one from end, after this, there may or may not be some zeros. So let's say there are some zeros. The moment you find n minus 1, the result is this. All these bits are the same. So the AND of this part and this part will be the same because it's a carbon copy. If you have 1 0 1 0 1 0 1 here and you have 1 0 1 0 1 0 here, the AND of this and this is going to be the same, right? But this part will vanish. So what means is that this one has vanished. Similarly, now what is the next set bit which is on? It is this set bit. So if you again take its AND with n minus 1, then what will happen? This set bit will vanish. So all the set bits would eventually end up vanishing one by one, one by one, one by one. And when all the set bits have vanished, the value of n will be 0. That is when you stop. And thereby you will get your count and you can just return that count. Make sense? So what will be the time complexity of this approach? The time complexity of this approach will be order of count of set bits, which is slightly better than log of n. Because if you remember log of n approach, there we were looking at all the bits. But in this case, the number of iterations of this loop is just going to be dependent upon how many set bits are there. So if you have a bit pattern which contains too many zeros and two less ones, then this is going to be a more efficient solution. Okay. This time complexity is log n in the worst case. Try to understand that point. It will be log n in the worst case. What will be the worst case? The worst case will be where your number is like this. If your number is like this, if you do n minus 1, you will get this, right? So in every shot, only one set bit will go away. So and please understand this point. The complexity will be log n in the worst case. In average cases, in most of the cases, it will be count of set bits. So it is definitely better than the previous solution, which was log of n. Why only the first one from back is getting toggle and remaining are the same? I mean, it's obvious, isn't it? See, I mean, understand it in this manner. Let's say you have a number which is like 110, 100. What is this? 4, 16, and 32, 40. This is 52, right? So I can write it as 110, 000 plus 100, right? Right? This 100 is not 100, it is actually 4. It is the sum of this and that. So when you are doing minus 1, imagine that minus 1 is happening from here. This thing stays intact. These bits stay intact. Only this is disturbed. So this 4 becomes 3. This is 48. This is 4. So now it becomes 48 plus 3, and that 3 is reflected here as 011. Understand the point? Okay. We could also have used this. Yeah, of course, but just see which approach is giving you the best time complexity. You could have built a mask. Yeah, we'll solve some question wherein you'll be using such masks. So let's quickly get on to something else. Another problem, very well-known problem. This problem is, I think maybe all of you would know about it, but still. So let's say there is an array in which every number comes twice. I'm sure the moment I write the question, you would understand. Every number comes twice, only one comes once. And you have to find that number. So what do? You take XOR of the entire array, right? Okay. So let's say you have 2, 1, 2, 4, 5, 5, 4. So what is the number here which is coming only once? It is 1. Okay. Now, the solution to this problem is to take XOR of the entire array, and it works. Why it works? Because I told you, if you're taking XOR of numbers, let's say A XOR B XOR C, you can take them in any order. B XOR A XOR C, in any order. So if you're taking XOR of the entire array, okay, in that case, you can imagine that just write them together. Write the similar numbers together. 2 XOR 2, XOR 4 XOR 4, XOR 5 XOR 5. XOR 1. This thing is going to be 0, right? Because 2 XOR 2, I mean, similar numbers taken XOR will be 0. This will be 0. This will be 0. And if you take the XOR of 0 with anything, if you're taking XOR of 0 with any number, the result is that number. This is pretty simple to understand. Because let's say the number is having a representation of this, and you're taking its XOR with 0. So what it means is that at places where you have 0, here, of course, you will have 0. So what you will generate at those places will be 0 for sure. And the places where you will have 1, you will get 1 here. Why? Because at those positions you will have 0. So there is difference. There is difference, right? So if you take XOR of a number with 0, the result is that number itself. Okay. So it means, coming back to this, if I take XOR of the entire array, all these numbers which are coming twice, 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 they will be dissolving to zero. And that zero, when XORed with the only number which was odd one out, will result in that number itself. So this is one approach which works pretty well. Now, if somebody changes this question and tells you that, let's say, uh, it's difficult to make notes and understand at the same time. Oh, okay. Probably we'll share notes, or maybe you can make little quicker notes, or maybe I'll arrange for notes. Don't worry. So let's say, yeah, now the question is a little different. So you have an array where every number comes even number of times. There is only one number which comes odd number of times. So let's say you have 6 and then 1 and then 6 again, 6 again, 8, 8, 6. Let's say it was 11. So every number is coming for even number of times. 6 is coming for 4 times. 8 is coming for 2 times. There is only one number which is coming for odd number of times. So can we apply the same approach here? Exactly. Exactly. Because see, if a number is coming for even number of times, its overall contribution in the XOR will be 0. The contribution of this also will be 0. So all of them will become a big 0. And when you take its XOR with the lone number which was coming odd number of times, so let's say this 11 came 3 times. Let's say this 11 came 3 times. No issues. Let it come 3 times. So the even occurrences of it will be 0. And one, this last guy will result in 11. So this is a generic approach to an array like this, where every number comes even number of times and there is only one number which comes odd number of times. Okay, great. Does this make sense? Do you guys understand that how XOR works in this case, how it kinds of help to solve this question? Okay, now we will take a little different question and you guys just listen to it carefully and just see how you would go about solving it. See, here the magic of bits works because if you understand the pattern of bits, you will be able to make a lot of things out. Okay. Uh, what if it requires to return odd number reputation? You mean repetition? How many times it has been repeated? Then the question becomes a little different. Okay. So okay, we'll try to probably touch base on that. For now, let's see one question. You have been given L and R. L could be anything, let's say 5, and R also could be anything. Let's say let's consider 17. So you have to consider, you have to pick a pair in between 5 to 17 with maximum XOR. With maximum XOR. So what does the question mean is that imagine you have numbers from L to R. So you have numbers from 5 to 17, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17. So out of these many numbers, you have to pick a pair of two numbers. It could be anything, maybe 6 or 15 or anything. But you have to pick a pair such that its XOR is maximum. That is what we want. So is the question making sense? How many of you understand the question? Diff set bit. Would you elaborate? Maybe you guys can have some examples if you'd like to. Let's say L is 3, R is 6. What will be the answer in this case? What are those two numbers which would have the maximum XOR? 3, 4, 5, 6. 3 is this. 4 is that. Okay. 5 is this. And 6 is that. What will be the value of 3 XOR 4? 7. Yeah. How many of you believe that the answer will be 7 for this case? Yeah, if you use little, thoughts, you can quickly correlate that the answer will not be larger than 7. Why? Because all these numbers are having at max 3 bits. Now 7 is a number with all the bits turned on. So this is the largest XOR that you can get, luckily. So if you take XOR of 3 and 4, you get 7, and that is the maximum XOR. See, the brute force way to solve this question could have been that if you write a nested for loop, consider all the pairs, and then whichever pair gives you the maximum answer, that is your answer. That would have been the naive way to solve this question. But how can we do a little better? So yeah, I can see some of you are already thinking in the right track, but here there is one caveat. Yeah, so you can clearly notice that, hey, you would want to pick the two numbers whose so many bit positions are differing, isn't it? So many bit positions are differing. Because if so many bit positions are differing, then taking the XOR will result in one at those bit positions, and then that would increment your answer. Right? So this is what you want. But how to pick that number and how to go about it, this is the important thing to understand. Right? So let's do one thing. Let us just consider a sequence of numbers from left to right. Okay, I'm not taking a generic example, I'm taking a conceptual example. So if you look at it, your understanding will be crystal clear. Okay, so let's say there is a number L whose binary form is something like 1 0 1 0 0 1, something like this, and one more zero. Then if you do plus 1 to it, you will get 1 0 1 0 0 1 1, something like this, right? And if you do plus 1 to it, you will get 1 0 1 0 1 0 0. If you do plus 1 to it, you will get 1 0 1 what 0 1 0 1. And if you do plus 1 to it, you will get 1 0 1 0 1 1 0. And if you do plus 1 to it, you will get 1 0 1 0 1 1 1. This is what you get, right? Okay, let's do a plus 1 again. If you do that plus 1 again, you'll get 1 0 1 1 0 0 0. And if you do another plus 1, you'll get 1 0 1 1 0 0 1. Again 1 0 1 0. Okay, let's stop here. So this is my L, this is my R. Can you see through this and tell me that what are the two numbers which you would want to pick for getting maximum XOR? So let's say this is L1, this is L2, this is L3, this is L4, this is L5, this is L6, this is L7, this is L8, this is L9. So which two numbers would you love to pick to maximize your XOR value? Okay, so many of you are saying you will pick L6 and L7. Very good. And why so? 2 and 3. Okay, let's see what happens if you pick 2 and 3. All right. If you pick 2 and 3, what will happen? Can I say that because this prefix part and this prefix part are matching, so the first 4 bits will be 0? Can I say that? Yes or no? Right? The first 4 bits will be 0. Because you can see 1 1 0 0 1 1 0 0. The next 3 bits will be 1 1 1 because it is 0, it is 1, it is 1, it is 0, it is 1, it is 0. So it will be 1 1 1. So what is this result? This result is 7. But those of you who are saying this and that, what will be the result? Here you would say that, hey, the first 3 bits are matching. So if you take a XOR, in that XOR result, the first 3 bits will be 0. And then the next 4 bits will be 1 1 1 because this is 0, this is 1, this is 0, this is 1, this is 0. So do you see? They're different. So it will be 1 1 1 1. And what is this thing? This is 15. So clearly it is larger than that. So even if you enumerate all the pairs, you will see that this pair is giving you the best possible result. And can you tell me why? Why did you pick this pair? What was the intuition behind picking this pair? So let us just understand that step by step. See guys, whenever a number changes, I mean, whenever you add 1 to a number, so this number was just 1 plus that, right? Then lower bits change first, least significant bits change first, and most significant bits change last. Do you understand this thing? Right? Like you can see from here all the way till here, the most significant bits are same, like it is 1 1 1 1 1 1 1 1 throughout. It is 0 0 0 0 0 0 throughout. 1 1 1 1 1 1 throughout. Now, so it's a very important thing to understand, and you can understand it quite clearly. Like even if you enumerate things from, let's say, 1 to 10, right? So how does one look like? 0 0 1, then 0 1 0. This is for 2, then 0 1 1. So do you see that first this bit changes, then it's the next bit that would change. Like now if you go ahead from here, it will become 1 0 0. So first the lower bits change, and then at last the higher bits change. I mean, that is how the change kind of happens. Now, another thing to understand over here is that I can say one thing for sure, that if I have been given a number L and I have been given another number R, and if for some reason I know what are their, most significant bit positions. So let's say the most significant bit position is this and this. What position is this, by the way? This is position 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So if sixth bit is 1 here and sixth bit is 1 here also, then can I say that all these numbers would also have sixth bit as 1? Can I say that? It is guaranteed. It is 100% guaranteed that all these numbers would also have their sixth bit as 1. And see, why I'm telling that thing is because uh, if you have a number which is, let's say, 1000101, right? Now, if you go ahead and create another number which has same number of bits, there, even if you make everything as 1, by making this thing 0, this value will definitely be smaller than this. Why? We all know that. Because the overall sum of this is 2 power j minus 1, and this thing alone is 2 power j. Yeah. So 1 followed by all zeros is greater than 0 followed by all ones. That is the idea. So what I can say is that, hey, if the smallest number is having 1 at most significant bit position, then all these numbers below it would also have 1 1 1 1 1 over here. I mean, provided that this is also 1 here and that is also 1 here. Okay. Now, please do not confuse it with cases like these where you could have your low as 0 1 0 and maybe high as 1 1 1. So here, this, sorry, high could be 101. So here, this is not your most significant bit. Here, your most significant bit is this. And this itself is changing. This itself is changing. So probably what we can do is, we can start from the most significant bit position of this R, and we can see if the bit positions are matching. It's 1 and 1. That means everything is 1 1 1 1 1. So if you take XOR of any two number, it would never ever happen that this bit, what bit is this? Sixth bit, right? 0, 1, 2, 3, 4, 5, 6. It would never ever happen that the sixth bit is 1. Why? Because all these numbers are having sixth bit as 1. So 1 XOR 1 will never give you 1 over here. Now you move on to the next significant bit position. You see here 0 and you see here also 0. What does it mean? It simply means that everything in between would also be 0 0 0 0 0. Because see, if anything in between is 1 1, its value must have been greater than this, which is not possible, right? So I 100% know that the next bit position would also be 0 if you take a XOR. Similarly, when you come to the next bit position, again you see this is 1 and that is 1. So it means that the next bit position would also be 0. When you come at this position, you see that this is 0 and that is 1. Now this stops you. This stops you for a moment. So what you end up saying from here is that, hey, this thing is 0 here and this thing is 1 here. So there must have been a point where I would have gotten 0 followed by all ones. And after that, immediately, I would have gotten 1 followed by all zeros. Only then this is possible because see, you have a sequence of numbers which are starting with 101 and then 1010 dot dot dot, and the last number in this sequence is like 1011 1011 followed by dot dot dot. Then this part is constant. I mean, this part is same throughout, right? Now the transition from here to 1 would definitely have happened at a point where I would have gotten some number as 101 followed by 0 all ones. And after that, 101, because if you add 1 to this, you're going to get 1 followed by 0, 0, 0, 0, 0. Now I know for sure that the XOR of this and this will be maximum XOR. Why? Because the first 3 bits anyways will be 0. And if I choose this and that number, I know all the remaining bits are going to be 1. So this question is all about finding that what is the first place where the bit value of L and R are different. The moment I find that place, I have answer with me. Because I know that if this position is 5th position, my answer is going to be 1, 1, 1, 1, 1, which is nothing but 2 raised to power 6 minus 1. Okay, do you understand the point till here? How many of you get this idea that why this and this would give us the maximum XOR? So see, that's the beauty of it. Like when you see how the bits change, when the numbers change, you can relate to things like these and then you can conclude things. So this is a beautiful problem. So see, in this question, there is nothing special that you have to do. I mean, you can simply say that, I mean, depending on what the question says, let's say the question says that your number L and R are all smaller than 10 power 9. 10 power 9 is smaller than 2 power 31, I believe. Yeah. So what you can do is you can consider something called as a bit mask. Okay, what is this bit mask? This bit mask is any sequence of bit where one bit is 1. Okay, any bit can be anything, but we are going to pick something like this. 1 left shifted by 31. 1 left shifted by 31 for me will be at 31st bit it will be 1 and then everything else will be 0, 0, 0, 0. And now what I can do is I can take AND of this bit mask with L. So I can take bit mask and L. Okay. And I can also take bit mask and R. Okay. Now what is that? What clue that is going to give me is that if this particular value is, let's say, 1 and this particular value is also 1, that means at the 31st bit L also has 1 and at 31st bit R also has 1. So everything would be 1, 1, 1, 1, 1, right? And then what I'll do is I'll shift my bit mask by 1 unit to the right side. So I'll do bit mask right shift by 1 unit. So if I do it, now it will become a bit mask where this thing is 1 and everything else is 0, 0, 0. So now if I take an AND with L and AND with R, and if I see both the values are same, so either they could be 0, 0 or 1, 1. So if they are 0, 0, it means that you had a 0 here and you had a 0 here also. So everything else is 0 in between. And if you had a 1 here, everything else in the between would also be 1, 1, 1, 1. See, you take AND of something like this with a number, then you know for sure that all the other bits are going to be 0. Only if this particular bit is 1, the result will be non-zero. And if this particular bit is 0, the result will be 0. As simple as that. And why right shift? Because we want to inspect all the bits. So we started our journey from the highest possible bit, and then we moved on to the next and then the next. So how do you take a look at this? You take a look at this by considering 1 followed by everything 0. How do you take a look at this? 0, 1, all 0. How do you take a look at this? 0, 0, 1, all 0. Because if you take an AND of this with this. And if that AND result is 1, that means this thing was 1. And if you take an AND of the same thing with this and that result is 0, that means this was 0. And this is not possible because this number is smaller. And so let's say this was 0 and this was 1. So basically, that's the reason you are right shifting your mask by 1 unit each time. And then taking AND with L and R, you are getting a clue whether that bit position had 1 or it had 0, whatever it had. Right? From left, we are finding first different bit with the help of bit mask. Yeah, from the most significant bit, yeah, exactly, you are right. From the most significant bit, we are finding the first position where the bit differs. Just imagine your first number L uh, was something like 0001, 101, something like this. Okay. And then your R, it was a form 0001110. And here you had, sorry, let's say here again you had 1. Here you had a 0 and here you had a 1. So this position differed, right? Because this position differed, what it means that we would have gotten a number here, which would be of form 000110110, all ones. And right after that, I would have gotten a number which would be of form 1 followed by all zeros. So if I take XOR of this and that, I'm going to get the best possible result. So what is my agenda? My agenda is to somehow find this position. What is this position? The position where the bits differ for the first time. Bits differ for the first time. So what I did, I constructed a large enough bit mask, 1 left shifted by 31, and that bit mask would be 1 followed by all zeros. And imagine this is your 31st bit. So if AND of this with L is same as AND of this with R, does it mean that both these bits would be same? Of course, yes. Because if you are taking this bit mask and ANDing it with L, we know that all the other bits will be 0. Only if this bit is 0, then the result will be 0. And if this bit is 1, then the result will be 1. Similarly, if you take AND of this thing with this, all the other bits will be 0 because everything else is 0. Only if this bit is 1, the result will be 1. So just see, no, I mean, if this is 0 and this is 0, L and this will have the same value as R and this. But if this is 0 and this is 1, then L and this will be 0, but R and this will be non-zero because these weight positions are 1 and 1. So in order to detect that whether the current bit position are different or not, we are taking AND of this bit mask with L and R and comparing those results. Is it making sense why we are doing what we are doing? Yes or no? If the results are same, if the AND of this mask with L, mask and L, is giving you same value as mask and R, it means this bit, both of them are matching. So now you want to move on to the next bit. How do you move on to the next bit? By right shifting this by 1 unit. So if you right shift this thing by 1 unit, what will happen? It will become 0, 1 followed by all zeros. This time if you take AND of this bit mask with L, what will happen? See, this and this bit, which is this and this, will be ignored. Only if this is 0, the result will be 0. And if this is 1, the result will be 1. Similarly, if you take AND of this and this bit and these bits will be ignored. If this is 0, the result will be 0. If this is 1, the result will be 1. Again, you will right shift it by 1 unit. Thereby, you will get something like this. So now do you understand why we are right shifting? Right shifting is just like iterating from 31st bit to 30th bit to 29th bit to 28th bit to 27th bit all the way till 0th bit till you find the first bit position where there is a mismatch. Yes, so you put it right. This right shift is just to iterate from most significant bit position till the least significant bit position. Is it making some sense? Do you guys understand it? Yeah. So now this bit mask idea, which I gave you in this question, is pretty handy in solving, lot many questions, lot many different questions out there you can solve using the exact same idea. So we will pick one such good question, okay, before we kind of wrap it up. And it's a really good question, and it has been asked many, many times in Google and Amazon interviews. I might even have heard of it. The time complexity of this will be order of 32. Yes, you are completely right. Because we are just iterating on bit positions, and bit positions are very few, 32-bit positions, if it's a 32-bit integer. If 64-bit integer, then 64-bit. See, that's the beauty. That's the beauty, right? If you operate at the level of bits, your complexity is as low as order of 32 or order of 64 because these many bits are there. You do not have an integer containing 1000 bits, right? You have an integer having 64 bits at max or something like that, right? So if you operate at the level of bits, you come up with magical algorithms. Okay, how many of you have heard of this term called as Hamming distance? Okay, so whether you have heard of it or not, it doesn't matter. Let us take a question. So what is the question? The question is that we have an array of integers. Given that we have array of integers, we just have to find the sum of XOR of all the pairs. Let's pick this question. Just think about it. We have to find the sum of XOR of all the pairs. So this question is even available on LeetCode. Here the question is formulated in a little different way, but the essence is the same. It says that the Hamming distance between two integers is the number of positions at which the corresponding bits are different. Okay. So given an integer array, return the sum of Hamming distances between all pairs of integers in the numbers. For now, let's say if you look at this particular example, what they're doing is they are considering all the possible pairs. Okay, so the first pair is 4 comma 14. So they have found out the Hamming distance of 4 comma 14. And then the next pair, which is 4 comma 2. So they have found out the Hamming distance of 4 comma 2. And then lastly, they have found out the Hamming distance of 14 comma 2. So these are the only three pairs which are possible, right? And they have found that the Hamming distance of 4 and 14 was 2. The Hamming distance of 4 and 2 was 2. And the Hamming distance of 14 and 2 was also 2. So their answer is 6. So that is what it is. So basically, you consider all the pairs, find Hamming distance of every pair, and sum those Hamming distances. So let's say you have something like 3, 5, and 4. Okay, so how many pairs are there in this array? The first pair is 3 comma 5. So we want Hamming distance of 3, 5. And then the second pair is 3 comma 4. So we want Hamming distance of 3, 4. The final pair is 5 comma 4. So we want Hamming distance of 5 comma 4. Hamming distance is the number of positions where bits are different. So 3 can be written as 0, 1, 1. And 5 can be written as 101. So what will be the Hamming distance of 3 and 5? At how many positions the bits are different? So you can see that here and here, here and here, here they are the same. So the Hamming distance of 3 and 5 is 2. What is the Hamming distance of 3 and 4? So 3 is written as this, 4 is written as that. So at how many positions are you able to see that the bits are different? Very good, 3. And how about Hamming distance of 5 and 4? 5 is written as this and 4 is written as that, right? So there is only one position where it is different. So your sum is 2 plus 3 plus 1, which is 6. So is the question clear to everyone, what we are trying to find? How many of you are clear with the question? Yes, no. Okay, so one of you has suggested a brute force solution. The brute force solution could be to consider all the pairs. And when you have considered all the pairs, then your job is done. So you can just write a for loop for I equals to 0 to n minus 1, for j equals to I plus 1 to n minus 1. So currently your pair is, let's say, a of I and a of j. And now, yeah, so a lot of you are suggesting, yeah, very good, taking XOR. Yeah, I'm happy about it. So you can take a XOR of ai and aj. And after that, what will you do? You will check that how many set bits are there. Very good. Because as many set bits are there, those many positions would have been different in AI and AJ. Is that making sense? Yes or no? Like if you take a XOR of this and this, you are going to get triple one. So there are three set bits. If you take a XOR of this and that, you are going to get 1, 1, 0. So there are two set bits in this. What will be the time complexity of this approach? This part will consume n square time. This part will consume n square time. This part where you are taking the XOR, getting an answer, and then further checking the count of set bits. What is the complexity of this? Count of set bits. We just learned an algorithm to quickly find the count of set bits. The average case complexity of this is equal to order of count of set bits, right? In the worst case, it can be log n, where all the bits are 1, 1, right? So it will be n square into log n. You understand why I'm saying log n? Because just imagine that your answer was 1, 1, 1, 1, 1, 1, 1. So here, if you try to count number of set bits, the number of steps will be equal to the, to log n, where log n is the number of bits which are present over here, right? So if your results can be like 64-bit integer, it is n square into 64. If your result can be 32-bit integer, it will be n square into 32. Is it making sense? How many of you understand why the time complexity happens to be n square multiplied by this thing? Okay, can we do better? Can we optimize? If yes, then how can we optimize? So that is where we have to think little differently. So we have to think at the level of bits. Okay. So imagine you have some numbers. I'm writing those numbers in their decimal forms, in their binary form. Okay. So you have 1, 0, 1, 0, and then you have 0, 1, 1, 1. Then you have 0, 1, 1, 0, and then 1, 1, 1, 1. See, now answer me one thing. If you are considering any pair, if you are considering any pair, then there is a contribution of different bit positions. So here you have 4-bit integers, right? You have bit 0, bit 1, bit 2, bit 3. Okay. Can you tell me if I call this as my 0th number, first number, second number, third number? Then, okay, one of you is saying, can we find the number of ones and zeros at current bit position? Yeah, that's a brilliant idea. That is what we should be doing. So tell me one thing. For which of these numbers the Hamming distance would be due to a difference at bit 3? I repeat my question. For which of these pairs the Hamming distance would hold contribution of bit 3? Like if you take Hamming distance of 0 and 1, you can see that this bit is different, right? But if you take Hamming distance of this and this, you will see that these bits are same. Similarly, if you would have taken Hamming distance of this and this, you would have seen that this bit is same. So I can say that this particular bit position, which is bit 3, will only contribute if the first number and second number have different items at their third bit. So at third bit, if there is 1 here, there should be 0 there. And similarly, if there is 0 here, there should be 1 here. How many of you understand this point? So what I can clearly say from here is, if you consider a pair of 0 and 1, the third bit will contribute. If you consider a pair of 0, 2, the third bit will contribute, right? Similarly, if you consider a pair of 1 and 3, the third bit will contribute. If you consider a pair of 2 and 3, the third bit will contribute. So basically, I can say, if there is a collection of numbers where third bit is on, which is this and that, 1, 0, 1, 0, and 1, 1, 1, 1. And there is another collection of numbers where third bit is off, which is this and that. If I pick any one thing from here and another thing from here, the third bit will contribute. Can I say that? Yes or no? Of course, because any number picked from here will have third bit as 1, and any number picked from here will have third bit as 0, right? So when you take their Hamming distance, you will find the third bit to be different. So that will contribute to the Hamming distance, to the overall Hamming distance. Now tell me one thing. In this basket, there are two numbers. In this basket, there are two numbers. So how many combinations you will get? It's a basic rule of product. 2 into 2, which is 4, right? I have two numbers that can be picked from here. I have two numbers that can be picked from here. It's just a Cartesian product. You can either pick this with this or this with that. Or you can pick this with this or this with that. So if there are m numbers in this basket, m numbers in this basket, then the contribution of third bit is nothing but m into n. So this is the contribution of third bit. If you now have to somehow find the contribution of bit position 2, how will you go about it? Contribution. So see, bit position 2. This is bit position 2. This, 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 and that. Okay. So now there is a basket of numbers where numbers with bit 2 as 0 are present. Numbers with bit 2 as 0 are present. So the first number is this. And another basket where numbers with bit 2 as 1 as are present. So 0, 111, and 0, 110, and 111. So what will be the contribution of this? It will be 1 into 3 because the number of choices I can pick from here is 1. The number of choices I can pick from here is 3. So total number of combos will be 1 into 3. So the contribution of this bit is 1 into 3. Similarly, you can find the contribution of bit 1, contribution of bit 0, sum them up, and that sum will be your real answer. Contribution technique, does it ring a bell? So what we are doing over here is, instead of considering all the pairs, we are finding contribution of a particular bit position. That's it. Now imagine in your array, you have got multiple numbers, right? So let's say your first number is like 10101. The second number is like 01101, then 1111, then 01011, 00010. Now, think of it in this manner. You take a bit mask, which is 1 followed by 4 zeros. Okay. Now, this is your index 0 and this is your index n minus 1. What you are doing is you are doing mask and a of I. If this thing is 1, what does it mean? You tell me. If the bitwise AND of mask and a of I is 1, then what does it represent? It means that, yes, very good. It means that that particular position is having a set bit. Correct. And if it is 0, what it means? It means that that particular position is having a 0 bit. Now, if you are taking two counts, count 0 and count 1. Now, what we are doing is, if this result is 1, we are doing count 1 plus plus. And if this result is 0, we are doing count 0 plus plus. So once you would have iterated on all these elements, count 1 would have a value of 2, because you can see that there are two numbers whose this bit position is 1. And count 0 would have been 3. So we can immediately do answer plus equals to 2 into 3. And that would be the contribution of this bit position. What is this bit position, by the way? Is it B0, B1, B2, B3, B4? And after this, you would want to change your mask from here to here, 0, 1 followed by 3 zeros. Now you see what we are doing, why we are doing this thing? Because now if you take this mask and do the same activity we did, we will get to know that how many of these three numbers, these many numbers had 0 at this bit and how many had 1 at this bit. And you can do this translation very easily. You can just do mask right shifted by 1 unit. That's it. That's really it. After that, you can do it again. This mask will change to 0, 0, 1, 0, 0. And then again, you can take this and you can take its AND with all of these numbers. And you will get that how many of them are having 1 at this bit and how many of them are having 0 at this bit. Do you understand this approach? How many of you kind of get a hang, at least some hang of this approach, like how it's working? So what we did nothing special. We just worked at the level of bits. And that's it. It worked for us. So in reality, okay, what will be the time complexity of this? Yeah. So whenever you have a mask, you iterate on all the numbers. And how many times this mask will translate? 32 times. If the integers are 32-bit integers, 32 times. So the complexity will be 32 into n. If you have 64-bit integers, 64 into n, which is way, way better than our initial complexity that was n squared. So you see, like the key things that you have learned today, this thing is how you work at the level of bits. And before that, we saw the power of bit operators and how the bits change and all sorts of things.